So English notebook, there is the sterling.
Okay, yeah, that can go in the box
Okay.
and then that, yeah, perfect.
I did, yeah, my name's on it.
Good, good. Thank you. Okay, so welcome everyone to the last class. Thanks for the formal reports. So I will get these to the graders as early as today or tomorrow. And my plan will be, I'll ask the graders to have these marked before the final exam. So then I will bring your graded formal reports with me to the exam on, it's Friday afternoon or Friday evening? Was that what it is? Okay, and then the other thing I wanted to say is that I have now finished marking the assignments and I have in Canvas calculated your final assignment grade and then your final pre-lab and lab grades. And so please just have a look at all of your grades in Canvas and let me know if there's anything that you think is an issue, like a missing grade or an incorrect entry or something like that. So for example, we've had one case of a thermal waves lab being entered in a wrong position. And so we've identified that, but if you did thermal waves and you're expecting a mark there and don't have one, that might be your grade. So please just email me if you think there's any issues. Okay, and then just one final reminder that the final exam, you can bring with you a letter-sized piece of paper and you can write whatever you want on it, both sides, okay? And then you should bring a calculator. Graphing calculators, if that's what you like to use, are totally fine. Okay, any questions about those logistical things? All right, good. So I only want to cover one more thing, and it's not a difficult thing. It's more for fun than anything else. So we were talking about these numerical integration method, in particular, the so-called hit and miss method. And the idea was, if we had some coordinate system, x, y, and we wanted to integrate some function, y is equal to f of x, what we could do is we could draw our function on our coordinate system and define our x bounds to be our integration limit. So we're going to integrate from the x minimum up to x maximum. And so we want to know what the result is going to be. And so what we should do is we should implement, oh, this is not quite right. We should, if I want to get the total area underneath this curve, sorry, let me fix this. I shouldn't have a y minimum. I want to know the area all the way down to y equals 0. Okay, so this would be just times y max. Okay, but I can set my x range to correspond to my integration limits. And then what we're going to do is we're going to randomly generate pairs of x, y coordinates. The x points will be between x min and x max, and the y points will be between y equals 0 and y max. And when we generate this random coordinate, what we'll do is we'll check if the point that I generated lies below or above the curve. If it's above the curve, I'm going to call that a miss. And if it's below the curve, I'm going to call that a hit. And the ratio of hits to the total number of points is just proportional or equal to the ratio of the area under the curve divided by the total area. The area under the curve is just the integral of f of x, and the area under the curve, the area of the box is just this x range times the y range, which in this case is just y max. And so what we could do is we can generate the simulation. We could count the number of hits for the number of trials. And if we multiply that by the x range times the height, then that is an estimate of the integral. Okay, and so I should just fix this here. So this is going to be y max times the number of hits divided by the number of trials. And then what we said is the hit in this method is a bit like it follows a binomial distribution, because in a binomial distribution, what we have is probability of success P, and we have a number of trials N. And so what we could say is that the standard deviation of the binomial distribution is N, the number of trials, times P, the probability of success, times 1 minus P. And the part that was interesting to us is that the standard deviation was proportional to the square root of n for the binomial distribution. And then it turns out, because the integral has a 1 over n in it, you have square root of n divided by n, so you get 1 over square root of n. And so the uncertainty in our estimate of the integral decreases as we increase the number of trials. And we showed all of that in a simulation. So what I want to do today is I want to think about another method for implementing numerical integration. All right. So let's do Monte Carlo integration. Wow, you see people that I've never seen in here before. Monte Carlo integration method number 2. Okay, so who remembers how do you calculate the average value of a function? Average value of f of x over the range x equals x is from a to b. So we could plot that. Here's our x-axis. Here's f of x. We'll say y is equal to f of x maybe. Here's our lower limit, and here's our upper limit. And then we could just have a function of any shape. And so the question is, how, if I wanted to, using calculus, how would I calculate the average value of this function from a to b? Yeah, okay, so I'm going to integral a to b. What am I going to integrate? F of x dx. Okay, and then what else do I need? That's exactly right. So the average value of our function between the limits a and b is given by exactly this expression. Okay, so this represents, So what would this average look like on here? Well, it's gonna be sort of in the middle of this line, right? This line will be half the time below the average and half the time above the average. And so we could kind of estimate what that's gonna look like. I don't know if I'll get it perfectly right, but it's something, well, probably should be a little bit lower than that, I guess. Here, let's fix this up. Okay, so let's see, something like this. This is F bar between the limits A and B. Okay. Now, if this red line is half the time above the function and half the time below the function, then what we could say is this area here that I'm going to color, let's say blue, is kind of offset by this area that's above the function, which I'll color green. And so what F average does, F average places the red line such that the green and blue areas are equal. So another way of saying the same thing is we could say that the total area under the red line is exactly the same as the total area under the function, because the area under the red line is going to include the blue parts that aren't part of the area under the function, but they're going to miss the green parts. But because the red and green parts have exactly the same area, then the area under the red line is the same as the area under the function. So another way to do the same thing is to say, if this is y, x, and then this is x and y, what we could do is we could draw our function again, and it looks something like this. Here's A and here's B. And then we could draw our red dashed line, something like this, where this is also going to be A, and this is also going to be B, and this is sitting at F average right there. So this area is the same as this area. So let's notice that the area under f of x, which is given by the integral of f of x dx from a to b, is the same as the area under the red line that representing f average. And that area is given just by the height of the box, f bar, times the width of the box, which is just b minus a. And so therefore we require that these two are equal to each other. So if we can develop a way to calculate f average, then we just take that value, multiply by the range of x values, and that's going to tell us what the value of the integral is. Okay, so we want a Monte Carlo method for calculating f bar so that can be used to estimate the integral I is f of x dx from a to b. And what's nice about this is we could pick whatever we want for our integration limits, because that's just going to change the width of our box, and we can easily modify our calculation so that we incorporate that. Okay, so the implementation is the following. So the first step is we're just going to generate a whole bunch of random x values that lie between a and b. So generate random number, say xi, that lies between the integration limits. Okay, so we're going to generate a random number that's somewhere between a and b. Okay, in step 2 is we're going to take that random x value and we're going to use it to calculate the value of the function f of x. So calculate yi equals f of xi using the value of xi from step 1. All right. And then what we're going to do is this thing's going to repeat over and over and over again. And so each time we repeat this loop, like every time we go get a new value of x, what I want to do is I want to take this yi and I'm going to keep a running total of all the values that we calculate from f of x. So let's keep a running total of all yi values. So y total is going to be equal to y total plus yi. So the first time we go through, like we pick our very first value of x, for that first iteration, y total is going to be 0. And then we go and we generate x, we calculate this y1, and so now our y total is just going to be equal to y1. Then we go back, we generate x2, we calculate y2 is f of x2, and we add that to the y total, and we just keep going over and over and over and over again. So that repetition is step 4. So we're going to return to 1, and we're going to repeat n times. Okay. When we do that, at the end of our n iterations, we're going to have some value y total, and we have n entries that contribute to that y total. We can then calculate f average is y total divided by n, and that's just equal to 1 over n times the sum of I equals 1 to n of yi, or if you'd like, it's f of xi. All right, so that's really easy to implement. When we did the hit and miss method, we already established how to generate x values. We can always do step 2, because if we're going to integrate some function, we must know ahead of time what the function is. It's maybe really complicated, but it's still just crunching some numbers. Keeping this total, running total of the y values is possible, and then this is a trivial calculation at the end. So then we could say that our integral is going to be approximated as this B minus A times F average. And that's the whole thing. Okay. So I'm going to show you an implementation of this, but before we do that, let's think about this uncertainty analysis. How do we expect the uncertainty in our estimate of I to change as we increase the number of iterations? So we expect our uncertainty in our estimate of I to decrease as n increases. Okay, so by propagation of errors, we would say, let's see, since I is equal to B minus A times F average, then the uncertainty in I is going to be DI dF average times the uncertainty in F average. Okay, so what's DI dF bar? B minus A, and then we have the uncertainty in F average. So that's right. This F average was just calculated by summing up all the Y values and dividing by N. But how do you get the uncertainty in, like, I guess, what's the standard deviation if you have a big list of numbers? Yeah, that's right. So this sigma F bar, if we wanted the standard deviation, is equal to, well, it's 1 over n minus 1 times the sum of I equals 1 to n of f of x. Well, maybe I should just say, we could just say yi minus f bar squared, right? So this is the square of the standard deviation. So the standard deviation squared, let's say. So for large N, we could say 1 over n minus 1 is approximately 1 over n, and therefore sigma f bar is proportional to 1 over the square root of n for large N. And so this was the same as we had for the hit and miss method. Okay, so let's see if we could make this happen. So what I'm going to do is I'm going to share this laptop screen. So just want to make sure this is visible. It is. Okay. And let me see. This was opened a long time ago. Okay, it's still running, I think. All right. So the beginning of this is the same as we saw last time. All I'm going to do is import some modules. I'm going to use this random number generator to generate a random number between 0 and 1. And then here I'm going to make 10,000 of those random numbers, and then I'm going to plot the histogram of those values. And this is just confirming that we're generating uniformly distributed random numbers. Okay, so the function we're going to integrate is the same one we looked at last time. It's this weird polynomial, remember, of order up to x to the 8th and down to x cubed. The first thing I'll do is I'll just plot that function. This function happens to sit inside a box that's 1 by 1, so the unit square. And what we want to know is the area underneath that curve. What we'll do is we'll just do the integral exactly because it's just a polynomial, so this one's easy to evaluate. And if you remember, the value of this integral was 0.4816. Okay, so now we're actually going to do this F average method. So all we're going to do is n is 10 to the 4. So we're going to do 10,000 iterations. I'm going to set the values of my integration limits. They're going to be from 0 to 1 in this case, but they could be whatever you want here. And then we're going to make our random numbers. We're going to generate them between 0 and 1, our lower and upper integration limits, and we're going to generate 10,000 of them. Once we have that list of 10,000 random numbers, these are all the x values. We're going to sub them into our function, our polynomial, and we'll calculate 10,000 values of f. These are our yi values. Okay. And then one of the last steps will be to just add up all the values of yi that are in the list. And then our integral I is the integration range, b minus a, times the total, f total, or y total in our notes, divided by the number of trials. And so that's all there is to it. And this takes less than a second to run, 10,000 trials, and we got 0.4738. So whereas the exact is 4816, if we keep running this over and over, yeah, so there's 4836, so that's one that's a little above the true value. Okay, so what I'm going to do is I'm just going to plot now you can't tell, but this thick blue line is actually a bunch of individual points. There's 10,000 points corresponding to the 10,000 different values of xi that were generated and the corresponding yi values that were calculated. So anyways, this is just a plot of our function. And then the red line is the calculated value of f average. And so what that means is that the area under this curve is exactly equal to the area under the red line. And you could see that that must be the case because the curve does not include this area, which the red line does, but this fits exactly in here. And so this compensates. The red line doesn't include this piece, but it has this extra piece here and here. And if you add up these two, it exactly compensates for this missing area. And so that's how this F average method works. What we can do is we can, this is just the same calculation. We don't need to do that. But what we can do now is we can calculate the value of the integral using the exact method that we did above, but we could do that 5,000 times. And let's see, I think this will work. Let's see, will it work? So we're 10% done, 20% done. So it's going to calculate this integral 10,000 times, and then it'll plot a distribution of the values of the integral. That distribution will hopefully be peaked very close to 0.4816. Let's see if it did. So there's 5,000 entries in this histogram. 4816 is around here, and that's right around our peak. So that's good. And then this standard deviation is an estimate of our uncertainty in the value of the integral. I won't go through all of it again, but I did that process where we calculated the integral 5,000 times for n equals a bunch of different values. So small values all the way up to 100,000. This took, how long did it take actually to do this? So it started at 1:10 on one day. Oh yeah, it took less than 5 minutes. It took less than 5 minutes, but this is the standard deviation of the histogram as a function of n, and this is 1 over square root n dependence. So that if we replot this as the standard deviation versus 1 over the square root of n, you get that linear plot, and that confirms kind of what we calculated in our notes, that we expect our uncertainty in our numerical integral to go down as 1 over square root n. So if you want to, if you're sitting somewhere and you get some uncertainty in your integral calculation and you want to cut it down by a factor of 10, you have to do 100 additional, like you have to increase your number of trials by a factor of 100. Okay, and so that's how it would work. Good. Any questions? No. Let's see. We have some spare time, but I'm basically done, so we can stop. Now I guess I will just ask, are there any questions about anything course related, final exam, anything like that? No. Okay, well then that's where we're gonna stop. Thank you very much. I hope you had a good term. Yeah, oh yeah, you got some? Yeah.
Is there anything you would specifically recommend us focus on to study the final exam?
What I would do probably is I would, yeah, that's what I would do. So the practice exams are, you know, I've been teaching this course too long. So I have exams here from 2013, 14, and 15, and the solutions. And so I wrote all of those exams, and I wrote the exam that you're gonna write. So if you want to know like what kind of style of question are you expecting to see, I would take a look at these exams. Now, the one thing that I would say is, up until a few years ago, exams were always 3 hours long. And then there was this push to make the reading week we always had a reading break in the spring, but they wanted one in the winter as well. And so there's a week off in the winter now that eats up some class time. And so they recovered some of that by saying, okay, exams can only be 2.5 hours long, and now we're going to write exams on Saturday and Sunday. So these 3 practice exams were written for the 3-hour time slot. So roughly, I would say you would expect your exam to be like these ones, but -1 question or something like that. That's what I would say. And so if you flip through this, if you remember, like the very first thing we did at the start of the term was we did Fourier series. And so here's our Fourier series question. Here is blah, 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 blah. These are propagation of errors type questions. So there's propagation of errors. Here is some kind of circuit. Who cares about the circuit? But you're given some data and you're told that the capacitor voltage is V naught times e to the minus t over tau. So what you're supposed to do is you're supposed to linearize this data so that it could be fit to a straight line. And then it even says, okay, we're going to give you a piece of paper. Here's a piece of graph paper, plot the data, and then do a fit by hand. So obviously I don't expect you to we did the whole thing where we wrote down the beta matrix and the alpha matrix, and then you had to take the inverse of the alpha matrix to get the error matrix. And you do all this stuff. So if you read the question, you don't have to do all that stuff in here. This is about linearizing the data and so that you could plot it as a straight line. Okay, and then here's a Poisson distribution type question. So some probability distribution stuff. And then there was, here's 4 questions, pick 2 of them to do. And so your exam will be that kind of style as well. So you'll start with a set of questions that everybody has to do, and then you'll end by picking 2 of, say, the 4 remaining questions. So I don't know if it's exactly 2 of 4, but it's like pick some of the remaining questions to do. And so let's see, what kind of stuff do we have in here? So this is another probability type thing. So this is, my guess is this is probably using binomial distribution. This is something to do with calculating the mean, derive an expression for the uncertainty in the mean. Okay, so this is find an expression for the standard error. Okay, is what this one is about. And then this one says, what would you do if the uncertainty in each of the individual measurements was different? And so this is like talking about the weighted mean and the uncertainty in the weighted mean. It's not asking you to derive those expressions, but it's saying, like, tell me something about them. Okay. This is a question about chi-squared. So we just recently kind of did some kind of intuitive understanding of what chi-squared tells us. If you're sitting at the minimum and you vary a parameter so that chi-squared increases by 1, that amount that you moved, it is an estimate of the uncertainty, that kind of stuff. Like, what would you expect the value of when minimizing chi-squared, when doing weighted fits? Okay. Right, so some chi-squared stuff in class. Oh, so then Monte Carlo thing. So this one says, tell me something about, we use 2 methods, pick one of the 2 methods. So tell me something about either the hit or miss or the F average. So all of the exams are kind of like that, and there's 3 of them for you to practice. All 3 of them have all of my solutions, and so hopefully that gives you a good sense of what to expect when ours comes around. Yeah.
So you're using on these exams, so what we asked in our final,
I don't know. I don't think so. When I saw, did I say anything about? Not as far as I know. I think we've covered all of the same material that was covered in those 3 years. Yeah. All right. Anything else? Yeah. Oh, sure. Yeah. Okay, so let's stop here. So I can get that back up. All right. Is this is the part that you want? Yeah. Okay, so thanks very much, everyone. I will be around during the exam period, but you know, I won't necessarily be sitting in my office the whole time waiting for people to show up. So if you want to see me to go over anything, just send me an email and we can work out a time that's going to be convenient for both of us, and we can make that work. Okay, good. Thank you. Pick something up.
Just for the quarrel report?
Yeah. Yeah, thank you very much.
Oh, do you have student numbers on it, or?
No, that'll be okay. Your name's on it.